Hello. Thank you, Chris and Janet. I'm Hoppy Price from NASA JPL, and 2033. I have my bumper sticker. Is it even possible to have a human mission to Mars in 2033? So on Monday, Mike French posed that question on the panel Maintaining Momentum, and the panel cited a number of technology gaps. And then in 2019, the Space and Technology Policy Institute issued a report that specifically listed the showstoppers for 2033. So I'm going to describe a concept with the idea to eliminate those showstoppers. And just to be clear, this is not a NASA plan, and it's not a NASA study, but NASA is studying a number of options for humans to Mars implementation. But what I'm going to show is a JPL internal study of an alternate approach to try and look at things in a different way. So this is just an example of a possible mission. So I'm going to bring up my slides here. Okay, let me go back to the beginning. So I'm going to talk about a concept for a 2033 Mars orbital mission with a Venus flyby. And just to be clear, we're not talking about a landing, but just going to orbit around Mars as a pathfinder. So this is a short duration mission concept using conventional propulsion. So 2033 offers a unique opportunity for a 570-day flight time. That's 1.6 years. And conventional propulsion for Mars missions would have a lower performance than the advanced propulsion that most architectures are looking at, but it would be more near term. So, 2033 could be possible. And using conventional propulsion would have a lower development risk, would probably have a lower total cost for an initial set of missions to Mars. And then I think after an initial set of missions, the sustaining missions going forward might not be short stay missions, because the long stay missions actually have shorter transit times, plus longer surface stays to build up infrastructure and maximize the science exploration. Now, advanced propulsion could support a more capable series, say using nuclear thermal propulsions, maybe after an earlier initial set of missions. And, on-ramping advanced propulsion later would provide needed time for its development and qualification for use with crew. And the higher delta V capability that you could get from advanced propulsion could reduce the transit time for long stay missions. So this particular concept would utilize near-term technology systems. It would minimize the development and mission risk with less complex systems using current technology chemical propulsion with a common stage design and common engines. And so, looking at this rendering here, there's a Mars transit habitat. And this is really the key thing. It's like a space station module, but it would keep the crew alive and support them and have the facilities they needed for a 1.6-year journey to Mars and back. And there would be an Orion vehicle to take the crew up there and also for Earth return. And so the only other thing are these stages. And so what would these stages be like? They're a lot like the Titan II second stage or the Proton third stage. These are chemical biprop propulsion systems, space storable. They're not cryogenic. And so there's a long history with this kind of a stage. So these components would be launched in segments by the SLS and also commercial rockets, and they would be assembled in high Earth orbit or at the gateway. And then the crew would return directly to Earth in the Orion capsule at the end of the mission. So again, 2033 offers a unique short stay orbital mission, 1.6-year total duration. And so if this mission would be the first crew to travel to both Mars and Venus. And my idea is that this would not be a one-off, but a pathfinder for crew transport and landing missions to follow, perhaps as early as 2037. So how would this work? First of all, you would need to launch some of these Titan II second stage type things. There would be a conventional stage. They would have solar panels and also avionics, so they could operate independently of spacecraft, and they would have docking systems on them. So in this concept, in this example, there would be 4 Earth departure stages that would be first put into low Earth orbit, and then an SLS would put a return stage that we would want to send to Mars, and we need to use this to bring the crew back from Mars after they're in Mars orbit. And this is about a 100-ton stage, so that's why you need the SLS to launch it. And then we need not just one stage, but we need 2 of those stages sent to Mars. So we would want to pre-position these in low Earth orbit, ready to go. And then around 2 years before we're going to send the crew to Mars, in the early Mars opportunity, this would be 2031, uh, these commercial stages would send these 2 Earth return stages to Mars. They would use their own propulsion system to go into orbit around Mars, and they would be remotely docked together to form a stage 1 and stage 2 as the Earth return stages. So then we need to get the transit vehicle for the crew going to Mars. So there would be 3 more of these commercial launches with these Titan II upper stage type vehicles to be positioned in low Earth orbit. And then an SLS would launch the crew transit vehicle. And so this is the transit hab plus an Earth departure stage and a Mars orbit insertion stage. And then those 3 boost stages would send that crew transport stack from low Earth orbit up to high Earth orbit. So now we're kind of ready to go. We've got the transit vehicle in high Earth orbit, and we've got these 2 return stages in Mars orbit. So now it's time to set up the crew. And this would possibly be a week or 10 days before the departure window for the Mars mission, so they could dock with this stack in high Earth orbit and get ready to go. And then when it's time to depart, the Earth departure stage would send this stack to Mars. It would be about a 200-day journey, and then they would use the Mars orbit insertion stage to go into orbit around Mars. And then they would meet up with the 2 Earth return stages and dock to that. They would spend about 30 days in Mars orbit, and then they would use the 2 trans-Earth injection stages to go back to the Earth. And it's a lot of delta V for this short stay mission. And not only that, but they need additional delta V by doing a Venus flyby. So they would actually go in to the inner solar system, go by Venus, do a Venus gravity assist. And because they would be in the inner solar system, they would need to deploy a sunshade to protect the vehicle stack from the higher intensity of solar radiation as they get in closer to the sun. And then they would go back to the Earth after a total of 570 days in space, and they would do a direct entry with the Orion capsule. And they would land, in the ocean, very similar to the Apollo astronauts. So I'm going to talk a little bit more about the sunshade for going into Venus. So going inside 1AU, a sunshade would need to be deployed to provide thermal control. And that sunshade would have to be pointed towards the sun to shade the crewed vehicle stack. And the solar rays would actually have to be tilted off sun, maybe by 45 degrees or 60 degrees, depending on their distance from the sun, so that they don't overheat and they stay within their specification. And there would be brief periods where they would be pointing off sun for trajectory correction maneuvers, or if there was an off nominal pointing event, they need to be able to survive that and get back to sun point again. And so I think this risk is reduced by using non-cryogenic propellants, having the space storable propellants. And there is a risk trade-off of doing this Venus flyby versus going for the longer 2.6-year traditional conjunction class mission. So we had a panel discussion yesterday I thought was pretty interesting on the short stay versus long stay. And just to recap a little bit of that, there are long duration and short duration options for 2033. They're both good opportunities. 2033 is a great year for Mars missions. But the short duration mission is 570 days versus 950 days. But it does require this larger Mars departure delta V. It's 3.3 kilometers per second of propulsion versus 1.1 kilometers per second for the long stay. So that's why you would have to position these large Earth return stages in Mars orbit in order to do the short stay. Example of a mission. So this is kind of all of the launches you'd have to have, and it's a lot of launches, but really when you look at any of the Mars architectures people talk about, there are a lot of launches, both SLS and commercial vehicles. But you'll see that these blue stages here, there are 11 launches that are actually, they're all identical, they're all the same. They're the 60-ton class hypergolic stages. They're launched on commercial vehicles. And then we have 2 of the 100-ton stages that would be put in Mars orbit for the return. And then there's 2 smaller stages that are used for Earth departure. And so the idea is that these stages would all be the same design, the same engines. They would come off the same production line, but there would be 3 different tank lengths. So for the different sizes, there's the 100-ton version, the 60-ton, and the around 40-ton version. And one advantage of this approach is that the transit habitat in these stages are all integrated together and fueled on the ground. So they're ready to go. They don't have to dock with anything except the boost stages. And then finally, there's the SLS launch with the crew. So if we were going to pull this off, what needs to be developed? What are the critical things? Well, the most critical item is the Mars transit habitat. And again, the most challenging thing, I think, is the life support system for the crew for 1.6 years. That's probably the tallest tent pole. And the idea here in this example is that a prototype could be tested at the Gateway in the late 2020s. Then you would need to have a production line to deliver the 15 hydrazine NTO common design stages. That would need to be established. And the production rate would be about 4 per year. The first flight would be in 2029. And you could order a few spares to protect against problems. In order to pull this off, the SLS Block 2 would need to be available by 2030 with a flight rate of about 1 launch every 6 months. And then commercial launch vehicles equivalent to Falcon Heavy would need to be procured with a flight rate of about 4 per year. And then are required for the longer mission and for a thicker heat shield for the direct Earth entry. And really, Lockheed Martin was looking into this for their Mars base camp concept. And in fact, this example of an architecture is kind of like a very minimal version of Lockheed's Mars base camp. So in conclusion, 2033 offers a unique opportunity for a short duration Mars orbital mission to minimize deep space exposure time for the crew. It would be a pathfinder to retire risk for the vehicles and systems to be used for follow-on missions that would land crews to explore on the surface of Mars. This concept uses low-risk, current technology systems that would reduce the development risk, cost, and the in-flight risk. And I think what's nice is that out of the 15 launches, the 11 commercial launches, they're all identical vehicles. So it would be easy. And Venus, which is pretty exciting. Just as I have a few extra minutes here, so I just wanted to show what a landing mission might look like, a follow-on. So what you see in this diagram here is the orbital mission that we saw earlier. It's the same thing. But now to land on Mars, what else would you need for a follow-on mission? Well, there would be 1 commercial launch to send a MAV boost stage to Mars. It would put itself into Mars orbit. And since we have a lot of use aerobraking to aerobrake it to low Mars orbit. And the purpose of this, as you'll see later, is to boost the Mars ascent vehicle back into a high Mars orbit after the crew does its mission on Mars. So then we need a lander, and SLS could launch an Earth departure stage and a lander to go to Mars. And since this lander has a heat shield, it could actually aero capture into Mars orbit. And so now we have all the vehicles we need. We have a MAV boost stage, we have the lander, we have Earth return stages for the short stay, and then we have the crew ready to go in the same kind of crew stack they had for the Pathfinder orbital mission. So the crew would go to Mars, go into orbit, they would meet up with the lander, the crew would transfer to the lander and land on the surface. And while they're there, it would be nice if they had like a car to drive around in. So we could actually have a commercial launch deliver around a 1.5 ton unpressurized rover. And that could actually be delivered by a sky crane, similar to Curiosity and Perseverance. It's that class of a vehicle, so that the crew could do some significant exploration and search for past life on Mars while they're there for a couple of weeks. Then the Mars ascent vehicle would take the crew to low Mars orbit. They would use the boost stage to take them from low Mars orbit back up to high Mars orbit. And then the rest of the mission is the same as the orbital mission. They would do the Venus flyby and return. And so that's the end of my presentation. And let me get back into my presentation mode here. Okay, so I can take a few questions here. And so there's a question about trajectories going clockwise versus counterclockwise. Yeah, people look at the trajectories in a different way. And then the SLS Block 2 at a 6-month tempo. That's actually the plan for the SLS in the time frame of the 2030s is to launch it twice a year, once every 6 months. And so in this example, an effort was made to time the SLS launches to be one every 6 months. And let's see, why would we use the SLS? It's because of these large payloads that you need. You know, you need a 100-ton stage launched into low Earth orbit. The crew stack is about 120 tons. And so that's really the only vehicle that can send something that size into Earth orbit. And then for things that you're sending directly to Mars, it just gives you a lot more throw weight to be able to send the vehicles there. So to try to break this up into systems that could be deliverable by the smaller commercial vehicles, I think it would just become so much more complex. So I really like the idea of the SLS as a mission architect because it enables you to get the heavy things that you need into orbit and to Mars. Let's see, another question. Are we too far off for permanent stays? I think so. I mean, you have to walk before you can run. You know, just as Apollo did things in stages, I think human Mars exploration is probably better off done, you know, in small steps rather than just trying to do everything from the beginning. And let's see. Oh, 12 year 12 student in Australia going to university. How can one contribute to the Mars mission? Well, I think part of it is just being part of the Mars community, like Explore Mars, the Humans to Mars Summit. I know I was very inspired by the Apollo missions, and to me, a lot of the reasons why we would do the Humans to Mars is really, besides the science, it's the human adventure and the inspiration, and certainly Apollo inspired me to pursue math and science and to pursue technical careers and the career that I have now. And going to university, contributing to a Mars mission, these days there's all kinds of opportunities for getting involved in small sats, you know, different space studies, projects. You know, NASA and aerospace industries bring on interns, you know, college age interns. And at JPL, you know, we've even had some high school interns. So clearly there's a lot of opportunities, I think, to get involved in the space community and contribute to the effort for humans to Mars. So I don't see any more questions. So I don't know if we're going to go back to the regular program now. Another question. How will we keep the astronauts the right way up because there's no up or down in space? Well, I think one of the things that crews learn starting in Skylab is that even though you're in zero G, when you're in a room, you tend to arrange the room so that visually there's an up or down and that people are kind of working on the same level and all the workstations are oriented the same way. So you don't have like one person working on the ceiling, the other person working on the ground. You know, I think a lot of our experience in ISS has also enabled us to figure out how to get around these issues of disorientation from lack of gravity. Is there any critical distance between Mars and the Earth for interstellar mobility? I don't know. I don't understand that question. How do you reference ISS for the future positioning of interim stations? Well, I think ISS is a great proving ground for things that are going to happen with the Gateway. The Gateway is like a small station around the moon, which is another step towards the human expansion into the solar system, having you know, a way station around the moon. So ISS is definitely a step along the way for creating other outposts in orbit around the moon or on Mars. So I'm not seeing any more questions here. Okay, I think I'm ready to wrap it up then. Okay, so that's it for my presentation. Again, this is just an example of a concept for an alternative approach for possibly doing a human mission to Mars in 2033.